Absolute valued functions are functions which involve a modulus. And what we do know is that everything inside the modulus turns out to be positive. So when it comes to drawing graphs of absolute valued functions, everything below the x-axis is reflected above the x-axis. That is, it turns out to be positive. So let's say, for example, we are drawing the graph of y equals modulus of x. So the first step will always be drawing the graph inside the modulus. And to draw any graph, we need 2 points. So in this case, when x is 0, y is 1, y is 0. And when x is 1, y is 1. So first of all, let's draw the graph of y equals x. And this would look something like this. Now the second step would be to reflect everything below the x-axis above the x-axis. So the graph would look something like this. And make whatever is below the x-axis dotted. So this is what the graph of y equals modulus of x looks like. So the sequence of steps of drawing graphs of absolute value functions are as follows. So the first step would always be to draw the function inside the modulus, followed by applying the modulus. And then once you apply the modulus, apply the sign before the modulus, which if it is positive, there will be no change to the graph. But if it is negative, the graph will be reflected about the x-axis. And finally, the last step would be to shift the graph vertically upwards or downwards based on what is outside the module. If there is anything. So let's take for example this. First of all, draw the graph inside the modulus, and obviously preferably draw it dotted, and also make this table. Since to draw any graph, we need 2 points. When x is 1, y is 1, and when x is 2, y is 2. So this is what we have. And then apply the modulus. So this will look something like this. Make the graph below the x-axis dotted, so it would look something like this. And then shift the graph vertically upwards. Uh, this would be the final step, so it will shift vertically upwards. So this point will also go vertically upwards, and this point would also go vertically upwards, making the graph look something like this. And the graph in blue is our final graph, and label this as answer, and also as y equals modulus of x plus 3. And the graph in yellow and all the intermediate graphs should also be labeled. And then our second graph. In this case too, the first step would be making the graph of x minus 1. That is the graph inside the module. So make this table. When x is 0, y is minus 1. When x is 1, y is 0. So the graph would look something like this. Or rather make this with some other color, like yellow. Then The second step is to apply the modulus. Everything below the x-axis is reflected above the x-axis, making the graph look something like this. Make the graph below the x-axis dotted or erase it completely. And then, what's the sign before the modulus? It's negative. That is, everything will be reflected above the x-axis. So this graph would look something like this. Let's make this video. It's reflected about the x-axis. And when something is reflected about the x-axis, every single point is reflected about the x-axis. So, is there something afterwards? Yes, it's true. And appreciate the fact that it's the same as this. Both these functions are the same. So, since we have plus 2 outside, this means we have to shift it vertically upward. So, this means that every single point would go vertically upwards by 2. Let's make the final graph with blue. And this is what it looks like. And then finally label these intermediate graphs. So the one in red would be y equals x minus 1 modulus and a negative sign outside. And this graph would be the one with yellow, y equals modulus of x minus 1. And the final graph would be labeled as answer and as y equals 2 minus x modulus minus 1. So our last and final example, I hope. No, wait, it's our second last example. So the first step in this case would also be to draw this graph. Make this table. When x is 0, y is minus 2. When x is 1, y is minus 1. So this graph should look something like this. You have a point here and a point here. Something like this. Extend this graph and then apply the modulus. So this point would turn out to go above, and this would look something like this. And bear in mind that this graph is not to scale since the axes are not accurate. So, and also make the graph under the x-axis dotted. Erase it. We have this, and we have a negative sign before the module. So make this graph dotted too, and reflect this about the x-axis. You make this with red, this graph would look something like this. And then finally shift this graph vertically, three spaces vertically upwards. And we all studied translations in AS. The final graph would look something like this. This and this. And finally label all the graphs. The graph in red is of y equals minus modulus of x minus 2. And the graph in yellow is of y equals modulus of x. And then the last and final. The first step is again drawing the graph inside the modulus, followed by applying the modulus, then apply the sign before the modulus, which is positive, so there is no change, and then applying the relevant vertical translation. Make this table. Since to draw any graph you need 2 points. So for the graph of x plus 1, when x is 0, y is 1. When x is minus 1, y is 0. So we have this and this. And then apply the modulus. Hmm. So everything below the x-axis is reflected above the x-axis. Hmm. So this goes here, and we have something like this. Make the graph below the x-axis dotted, and then there is no sign before the modulus, so no change, and then apply the vertical translation of two spaces downward. This would look something like this. Wait a second. On my ease, I'll shift this graph downward. So shift this graph vertically downwards, and we have something like this. Yeah, this and this. And again, the final step is to label the graph. This graph is the final graph, so labeled as answer and also as y equals modulus of x plus 1 plus 2. And the yellow graph would be labeled as y equals modulus of x plus 1. This graph would be labeled as y equals x. And this is one of the easiest chapters there can be.